Hi everyone. We will start in a few minutes. So, in the meantime, if you want to check out the paper or the Google Drive, sorry, I have to manage access. Okay, it should work now. Let me do it again. Okay, now it should be working. Our guest speaker will be arriving any minute. I guess in around 2 minutes or so. So yeah, in the meantime, please check out the paper and the presentation. And yeah, looking forward to having this discussion. And if you want to leave comments in the chat or come to the stage, feel free to raise your hand. And yeah, will be fun. Happy Friday, everyone. Yeah, also, if you think that this is like a worthwhile discussion, feel free to share the room. And yeah, we'll be starting soon. Yeah, hey everyone that just arrived. We will talk. Our guest speaker will be arriving any minute, and if you want to check out the paper ahead of time, again, it's open source. It's in the chat, the link, and yeah, check out the presentation. Everyone should be able to access it, and yeah, looking forward to the discussion with everyone. Feel free to raise your hand, come to the stage, participate. It's always more fun if people chime in with questions, so feel free to do so. Thank you. Hi Murat, how are you? Welcome, welcome. We'll start around 2 to 3 minutes, so you still have a little bit of time to relax. And happy Friday. I think I forgot earlier to say happy Friday. Yeah, yeah, I can hear you. How are
Perfect.
you?
Okay.
Yeah, we still have 1 or 2 minutes. I hope you're having a good Friday, not stressful.
Oh yeah. It is going nice. I hope it's the same on your end too.
Yeah, it's all good this Friday. And the weather is surprisingly good still this September here in New York, so that's also nice. So
Oh yeah. Same in Boston. I mean, we often have very similar weathers with New York, anyways. I guess, but it is surprisingly pleasant today, indeed.
yeah, I don't know if in general it's a good sign, but personally, right now, locally, it's a good sign for my
Fair
mood.
enough. Fair
Yes.
enough.
So yeah, and also welcome everyone. Please check out in the chat. There's the link to the paper, and yeah, you can find the link to the presentation on top. Uh, so if you're interested in learning some more, yeah, please check out the paper again, and also we can feel free to direct message me with more information and so on. So great, I think we can start. So welcome everyone to Science Society, to today's room, and of course a special welcome to you, Murat. And thank you so much for coming and going through the trouble to make a an account and everything to come here. It's really an honor, so really appreciate it.
No, I
And
mean, thank you very much for inviting me. This has been a pleasure, and I hope I can give an interesting enough presentation to everyone. And yeah, looking forward to it.
oh, for sure, it will be for sure really interesting. And yeah, so before we start, let me give the audience a little bit of an introduction so they get to know you a little bit. And then we usually ask a couple of small interview questions to get like some conversation going, and then it's time for your presentation. And yeah, we'll go from there. So Dr. Murat Omen, he he did his bachelor at the Middle East Technical University. It's just a coincidence, but we had earlier this week also a researcher that did his bachelor at the same university. Interestingly, it's about material science, food engineering, using different laser types to combat germ resistant microbes in food. So
Wow.
anyhow, so I should introduce the two of you. And yeah, then Dr. Onen, he did his Masters of Science at the Massachusetts Institute of Technology in Electrical Engineering and Computer Science. And he also did his PhD there in electrical and electronics engineering. And he's now a postdoc at MIT. And did a lot of really interesting work. He also at some he did also some research at as an intern at IBM, the Watson Research Center. That sounds like it was also for sure very interesting research, and it's a pinchy that Serena is not here because Serena also did research there at some
Oh,
point. So, but she will listen to the replay for sure. Maybe she'll make it a little bit later. And before we start, we usually ask if you could let us know if like was it always something you wanted to do to kind of do research, become scientist, engineer, or was it something that maybe some teacher, some book, or some experience triggered that interest in pursuing a career in the field?
that's an interesting question. I mean, it has two parts to it, I guess. I mean, A, which is the more common answer, I guess, is yes. I mean, science has always been a part of what I like doing, and I'm also what I happen to be good at. So, at least that was a good synergy. You know, what you want to do and what you're good at, them aligning is an advantage to have in this life. And so I always liked science, even from a very young age. I was actually very interested in biology to start with, particularly different herbs and how they interacted with people, what are the chemicals inside them. As I continued in the school, around middle school and high school, I got obsessed with chemistry. I was actually in the chemistry Olympiads, and what was yeah, like at those times I was quite certain that I would have a career in chemistry. But then the reality of life, at least in Turkey, where I was born and lived for over 20 years, I guess, was chemistry was not the best career option at the time. So that is how I ended up in engineering instead, because we had I don't know how it is in different countries, but at least in Turkey we have this general exam, and then you get a score and get a ranking, and according to that you get into your university. And electrical engineering was the top, at least electrical engineering, medicine, and law were the top three, I would say. And I didn't want to become a lawyer, and I didn't really want to become a doctor, not a medical doctor at least. So I picked engineering. That's how I started. How I continued research from then on has few parts to it. In undergrad, I was already doing some research. As you said, I went to IBM once, which was a fantastic experience. And even in the during the bachelor's degree, there was a young researcher program that I got into. So I realized that I liked doing research from that point of view. But also I can't skip without saying that there was a more political component into it as well. As in, I wanted to get into the world, get out of Turkey a little bit due to some of the conditions that I was not a particular fan of. So as a researcher, you do have more opportunities, I would say, than any any employee fresh out of bachelor's. So applying grad school was a nice way of getting into a new country and starting a new experience from start. So that's why where I became certain that I wanted to do research. I already liked doing it, so it was not just for the sake of living anywhere, but uh, that definitely was a contributor to the fact that I wanted to go to Europe or go to the United States, and indeed I ended up in the United States, where I'm quite happy now. So yeah, I think even if I didn't become a researcher, I guess I would still be doing science related things, I guess, or maybe math. But because those were the things that I always found most enjoyable. But yeah, at least in the in the decision that made me join a PhD program, there was more than just idealism. I must admit, it was not just pursuing an ideal, which certainly had a portion, but not all of it. And now that I've finished my PhD, I'm liking it more, to be fair. And these days, I'm also interested in a bit more maybe the entrepreneurial side of science. How do you commercialize a scientific output? And I would love to talk about that if that is of interest. And yeah, that's where I am now. I'm currently continuing as a postdoc, and looking forward what's going to come next.
Yeah, thank you for sharing that. And I think it's the ideal world situation where you can combine like your passion with also what's good for you, right? And with like things you want to do and try out. So I think that sounds like you did perfect choices, and congratulations, you have the life you wanted to have. That's already a huge achievement. So that's wonderful.
Thank you.
And the second question would be, how did you choose the specific field and research, and also this project? Like, was it hard? Like, did something like special happen that this project came about, or was it really easy and pretty straightforward? Was it hard or easy to get grants for it? Like, did people believe you could do it? Like, like, I know it's probably two questions merged in one, but I think it's always really interesting to peek behind the curtains a little bit of how projects come about. Thank you.
Yeah. No, it's a good question. So, how I initially entered into this field was in actually in this internship that you mentioned earlier. It was in 2016, I believe. And that was not entirely by choice. I was doing something in the field. What I was doing in my bachelor's, I was conducting some research based on how can we mimic some of the dynamics that exist in neurons and its support system in order to get some phenomena out of there and apply them to AI. But I must admit that it was a very premature effort. I mean, I was a bachelor student anyway, so it was not really an advanced research per se. But that led me to get into this internship where they were starting to work on these analog architectures. That was a bit of a chance, I would say. And they were doing that. They asked if I would be interested in doing that. And to be completely honest with you, whatever they could suggest me, I would have jumped on it anyways. Because I was a undergrad student in Turkey, and this was a big opportunity in IBM research at New York. So, irrespective of the project they would propose, I would have probably accepted it. But they happened to propose this one, and I started from the algorithm side of this. And actually, at part of this talk, I will mention them too, and the algorithms for these new type of processes. And that's how I got into the field. After that, I did my master's in actually in superconductivity, an entirely different field. And the reason I got into superconductivity was I was thinking, uh, maybe I got just lucky and got in, because when I got admitted into MIT, I was definitely thinking, oh, do I really deserve to be here? What did I really do enough to get in? I didn't know, so I wanted to get into a field where basically you don't know anything about, such that I was thinking if I can survive this, that would at least prove that I am worthy of something. And lucky enough, when I clearly admitted this to the professor who I was going to work with, he was okay with that. So, and I indeed survived. And actually, my master's was, quite successful actually. Even though I'm not working in the field of superconductivity anymore, I did quite decent for a year and a half type of project. It was quite fruitful, and and right around those times, this project came up in with another professor at MIT. And since I knew what was the problems in the device realm of the same processes, so whenever you come up with a new processor, there are multiple parts to it, right? There are the building blocks, there is the system, and then there is the software. So I started from software, but I was aware of the issues in the devices, so all the way down. And this project was aiming to change that. They got this project, they had a proof of concept with a material that was not that good. I'm going to mention that in the talk as well. And they were intending to basically come up with this new device family that would enable realization of these processes. And that got me interested in, and at the time I was also willing to take a new challenge. As I said, I liked superconductors a lot, but I think throughout my career I always try to sample as many things as possible, because I like new things, I like new challenges a lot. So that's how I ended up in this project, and I joined it 3 years ago, and it went a long way during the last 3 years, and now I'm also seeing, okay, which next steps that I should be taking, to advance this one any further, or maybe something completely different. I don't really think so far, but like, to push this into a new realm such that it is new to me. I can continue learning new things about it, and yeah, so the project's funding was done by someone else. Essentially, they got the project, they needed a person to do it, and I was available at the time. And since I had the experience coming from at least another side of this field, they thought, oh, this is going to be a good fit. Instead of starting with a person, at the origin, this person at least knows something about it, not necessarily the devices, but something about it. So that's how it ended up being. I think. Hope that contrary story kind of gives an answer, but I think it was a very non-linear process, to say the least.
Yeah, that's but we have this you have this amazing results and publication and work. So in the end, all is perfect. So congratulations again.
Thank you.
And it's also, it keeps life interesting, right? If things are not straight forward,
Yeah,
and so um yeah, so the stage is yours for everyone. The presentation has been on top of the room, and yeah, we are all curious to hear your talk. Thank you.
awesome. Thanks. Well, uh, first of all, welcome everyone. My name is Mertanen again, and today I will be presenting you analog deep learning in general. So when I was thinking to what to present in this talk, I decided that, okay, if I just do devices, it's going to be too technical, maybe too dense, or if I do the algorithm side, again, maybe that way. So I tried to design the talk such that the first, maybe even maybe first half of it is quite high level, introducing the field, assuming no prior knowledge in analog deep learning, why it is, why it exists. So my goal today actually will be to show by the end of this talk why we urgently need better AI hardware, how can analog deliver that, and what are the necessary steps we need to take. And as I said, I will go through a relatively lengthy introduction to do justice to the introduction of the field, and then follow it up from the examples from my own research, which of some will include the results of the latest paper, and then I will also show some results regarding the algorithms work that I do. And I'm more than happy to stay for Q&A to, if there are any particular questions, maybe in-depth technical questions or rather general questions, I'd be happy to start. So uh, I will start with the slides starting from 2, and I will try to remind everyone which slide I am anytime I move. I hope I won't mess it up, but uh, anyway, so I first want to start with what makes deep learning so special, why we are so interested about it. So when you have abundant labeled data, which we do have today, and when you build complex connectionist systems, such as the one that you can see in the background of slide 2, at least an illustration of it, you can then train these systems to extract some properties of the data set, some underlying properties of data set, and then form abstract relations between them. So what do I mean by this? To exemplify, we can have a look at this network GPT-3. the state-of-the-art natural language processing network we have. And for those who are not familiar with GPT-3, you can think of it as a massively advanced Alexa or Siri, in the sense that it inputs questions in text form. So you prompt a query in a text form, and it also provides the answer in the text form. That is why they are often called as natural language processes. So when you ask GPT-3, why is bread so fluffy? It then returns the answer describing the details of the leavening process. And what makes this interesting compared to, say, finding the same answer in a search engine is that this network, GPT-3, actually has never seen this information in this explicit form. What it's doing instead is it's building a representation to associating many low-level futures that it learned during its training over a quite large set of examples. To put that into context, the entirety of Wikipedia was used to train GPT-3. And even that huge data set only comprised 3% actually of the complete data set it was trained on. So moving on to slide 3, you will see that it it's not going to surprise you that it was not an easy task, right? So to train this network start to end took 10 to 23 floating point operations, which is a very high number. And I want to note here that this number even excludes all the experimentations went into this in order to decide on the network structure, decide on the hyperparameter optimization, and so on. So this is the only last actual training that was done. And if you were to do this on a single high-end GPU, it would take 355 years, to converge. So obviously that's not what the researchers did, right? Instead, what they did was to harness enough compute power at the data centers in order to complete this task in a matter of few weeks. And while that worked, obviously, it also came with a hefty cost of $15 million. What we do know with almost certainty is that these numbers are going to go up. By 2025, estimations suggest that training the state of the art neural network is going to cost more than $1 billion. And not only that, it's also going to consume higher power than the entire New York City, which is quite mind blowing if you think about it. And what this means is, as we move on towards advanced AI applications such as autonomous systems, intelligent decision aids, or natural language processes, fewer and fewer people will be able to train these networks simply because they just won't be able to afford it, right? And as a result of that, AI will monopolize more and more. And ultimately, whoever has the best hardware is going to take it all. Which is why in slide 4, you will see a lot of different AI hardware has been proposed to address this issue. So this graph shows many different architectures presented with respect to their peak power in watts and peak performance in giga operations per second. If you move towards up and right in this graph, you will what you are essentially doing is you are giving more and more power to your processor, or you are maybe using multiple processes in parallel in order to have a higher peak performance. That's why you start seeing data center level systems. And instead, when you look more closely towards the origin, you start seeing edge processes or mobile processes sometimes, where the total amount of resources you have or you can allocate are limited. So you are trying to keep a low power budget while giving as high of a performance as possible. So in order to be able to compare these systems at very different deployment ends, right, all the way from mobile to data centers, people often use a normalized metric such that they are comparable, which is operations per seconds per watts. And you can see those dashed lines crossing across the graph, which are showing these values. And what we started seeing in the last few years is that digital CMOS-based architectures, which are basically the conventional architectures that we use for our computers, our mobile applications, and so on, they started to get limited by this 10 teraops per watt line. And this is a problem, considering that as I said earlier, if you want to move on to advanced AI applications, these kind of metrics are not enough, not going to be enough to get them in a reasonable amount of time, reasonable amount of energy, and reasonable amount of budget. And if you, on top of this, if you think about the diminishing returns we started getting from transistor scaling, the situation actually becomes quite dire, right? And that is exactly why analog processors started off becoming interest. So the point of the promise is more than a petaops per watt type of metric, and therefore they are extremely interesting to the engineering community on how to make them real. So, but let's take a step back to understand how this graph emerged, right? So in order to do that, let's have a look at what are the operations that we are trying to execute, why digital architectures are having a hard time doing them, and what is special about analog ones that make them more suitable for this application. So on slide 5, um, what we can see is bulk of deep learning actually comprises two key tasks: testing the inputs and updating the weights. So whenever you present an image, for example, of a cat to an image classification network and ask what this image belongs to, what you end up doing is a series of matrix inner products between the input image you have and the successive layers of the neural network. And when the network returns you the answer saying that the image belongs to that of a tree, then you need to update the weights. And to do that, you end up doing a series of matrix outer products such that the error is minimized. And the next answer will hopefully be more accurate. And these matrix inner and outer products, or matrix algebra in general, is particularly tricky to compute over digital architectures. And to understand that, we need to investigate what happens in slide 6. So first of all, whenever you want to do either one of these operations in a outer product, what you have to do is you need to bring the input matrix and the weight matrix from the memory and transfer that to the processor. And once the processing is done, you then need to write them back to the memory. So at the large scales of matrices that we are dealing with today, uh, this type of communication quickly exhausts the memory bandwidths we have, causing this infamous problem called the von Neumann bottleneck. But it doesn't end there. When the matrices are finally in the processor, it's still a very high computational complexity operation, specifically O n cubed. So what do I mean by that is, if you want to do the same operation with a matrix that is 10 times larger, you will actually end up doing 1,000 times as many operations. And obviously, if you have a serial processor, you need to wait 1,000 times longer as well. And there is obviously another way to do it. I mean, instead of using a serial processor, such as a CPU, we can use a parallel architecture, such as a GPU. And the idea there is we divide the same task into many parallel cores such that the operation is done again with parallelism, right? But the problem there is each GPU core, this unit element that we repeat to get parallel processing, is actually comprising of few hundred transistors. And given how many of them we need to parallelize, these architectures end up becoming highly area and energy intensive. And that is exactly where the analog processes come in if you move on to slide 7. So when we talk about analog hardware, it is actually very important to do spend some time on disambiguation, because in the last decade or so, particularly in the last few years, there's so many mentions of analog hardware, which we now need to spend some time to say which one, right? On the left, we can see the actual predecessors of the computers that we use today. I mean, they were analog at the end of the day. Before we had digital computers, we had analog computers. And these machines were essentially signal processors. They processed continuous variables such as light or electrical voltages and so on, or sometimes even mechanical versions. And what they did was to imitate complex systems. For example, the image that you are seeing on the left is it belongs to a pharmacokinetics simulator. So what it does is it simulates the motion of a drug inside human body. And the interesting part about that is, like, for at the time this machine was being used, if you were to try to do this on a digital processor of the day, they existed, they were in the early days, it would have taken you forever to, define the partial differential equations you need, then doing numerical simulation methods in order to converge to a result. It would simply be impossible at the time. But instead, when you did the same with analog components, where basically the dynamics of a drug moving inside human body were matched by the dynamics of the electrical circuit that you built, you could then simply energize the circuit and look at the particular parameters that you're interested in, and then infer decisions what they would mean for the motion of the drug. And on top of that, I wrote long past with a question mark, because while it's obvious that they were in the past, they are actually having a comeback in the recent years. But nonetheless, those are not the architectures that I will spend time on talking about today. So on the right side of the slide, you will see neuromorphic processes. And I'm quite sure many of you have heard this word extensively. And at the core, what these architectures are aiming to do is that they want to imitate neuroscience through mimicking the spiking nature of the synapses and how Hebbian learning takes place through the timing dependencies between those spikes. So, and on top, I chose to write far future, again, with a question mark next to it, because on one hand, I think it makes perfect sense to look at human brain or mammalian brains in general and see an incredibly powerful processing unit as the brain. It's very compact, uses low power, can achieve very complex tasks. So it makes very good sense to try to mimic that. But it turns out, if you only mimic what happens at the low level with these spikes and timing dependence and so on, it simply doesn't give us enough functionality today. So whenever we want to get any intelligence-like future, such as classification, for example, mimicking these neuronal dynamics, at least the ones that we understand today, are not enough. So one day they might, as we understand human brain more and more, these architectures will probably become a reality. But today, I think they are quite immature. So that is why I'm going to talk about intrinsic processes, which I'm showing in the middle instead in today's talks, which you might have seen or heard in the terms of resistive crossbar arrays. And what these architectures essentially are is they are efficient linear algebra machines. So if you move on to slide 8, to very briefly explain what they are doing, on the top you will find this sentence: local and fully parallel information processing using physical properties instead of Boolean arithmetic. And first of all, let's divide this into some pieces. These machines are local, or also called as in-memory compute type, in the sense that the physical place where the weight matrix is stored is also the exact same place where the bulk of the operations are processed. So as a result, whenever you need to do a matrix inner or outer product, you don't need to bring the weight matrix from memory and write it into the processor, as it already is in the processor. You still need to bring the input matrix and write back the activations. So you still do need some communication, but nonetheless, this approach drastically reduces the amount of memory bandwidth you require and partially resolves the von Neumann bottleneck that I mentioned for digital ones. Second, these are fully parallel architectures, and they can process matrix inner and outer products with O(n) computational complexity instead of O(n) cubed that I mentioned for digital. So then now if you scale something by 10, the time it takes is going to only scale up with 10 instead of 1000, which is great. And the most interesting part of these architectures is instead of getting this parallelism through many complex circuitries comprising hundreds of transistors each, they only do that by a simple and single resistive device element. So what you're basically doing is you're trading out a few hundred transistors to be replaced by this one resistive element. And the reason that they can do this is instead of trying to do these matrix operations with Boolean arithmetics or binary logic, so representing things with ones and zeros and employing logic gates with registers and so on to force this construction to process your multiplication or addition, they do these operations through intrinsic device behavior. For example, they do multiplication through Ohm's law, they do accumulation through Kirchhoff's current law, and possibly more interesting than both of them, they can also do rank 1 updates, which I'm going to explain what they are in a minute, to certain device physics and probability or statistics. So as a result, what happens with these kind of devices is they will be much more energy efficient because instead of paying a lot of overhead to complex systems such that you can get some functionality, you are now using some devices that naturally lend themselves to the application that you want to do. So that is the key idea, and that is why at least I call them intrinsic processes, because again, they intrinsically are working in the way that you want them to. So on slide 9, what you will see is the core, the heart of the analog processor, which is a crossbar array of resistive elements. So in this case, what you are going to do is that you are going to represent the weight matrix of a neural network layer with the conductance values of these crosspoint elements. And then when you represent the input vector as the row voltages, the resultant column currents will be simply the inner product between the row voltages and the conductance matrix. Really relatively simple idea. And the nice thing about this is if you double the size of this conductance matrix, it's still going to take the same amount of time, right, for the currents to result with respect to the application of the voltages. So in other words, the vector matrix multiplication that we are doing here is constant time, O1, and the matrix multiplication, therefore, is linear time, ON. And this is nice, but on its own, it's just simply not enough, because in order to capture a deep learning application or training application, one also needs to be able to program all of these conductances in parallel. So just being able to read them in parallel is not enough. We want to program them in parallel. And in slide 10, you can see immediately that how this happens is significantly more complicated than the very simple physics that go in slide 9. But in 10, what I'm showing is what is the method that allows us to implicitly calculate and also apply all of these updates in a fully parallel manner. And it relies on two key things. One, probability of statistics, and two, device behavior. So probability side of the things is relatively easy to achieve because it is essentially governed by the peripheral circuitry. What we want to do with the probability is you see those pulse trains at the rows and columns. We just want to be able to assign the probability uh, proportional to the value we want to have. Sorry, that was a bit confusing. I'll take a step back. Uh, what we want to do is to generate those pulse trains where the probability of having a high value is proportional to the value you want to use for the rank 1 update. Might be a bit too technical here, but that's what we want to do, and that's relatively easy to do because it just is some circuitry. We have that, no problem. Instead, the integrity of this operation, as you might already imagine, heavily relies on this device behavior. So if we have these devices acting in a certain way, the update will be accurate and nice, such that we can train these conductance matrix representing a neural network. But if they don't, then the update you are doing essentially has nothing to do with a neural network training. So then, of course, that's a big problem. So let's look at slide 11 now to see what are those device properties that we want to have. So we want to have a device with a conductance value, and when we apply a positive voltage pulse to this device, we want this conductance value to increase by just an incremental amount. And then when we do another voltage pulse, increases a little bit more, another one a bit more, so on and so forth. And then when you invert the polarity of the voltage pulse to a negative one, we want the device conductance to decrease, again, by a tiny amount. Another negative voltage pulse decreases further, so on and so forth. So, and if you don't apply any pulses to this device, we want the conductance value to stay exactly where it was when it was programmed to last time. So that's why these devices are often called as non-volatile programmable devices or non-volatile programmable resistors. And you can see the shape that we are looking for on the left side of the slide for an ideal device, where we want a gradual change, preferably linear change. It doesn't have to be linear, but we want it to be preferably linear. That helps. And definitely symmetric. So by symmetry, the way we define it at least is when you do an increment and a decrement, it should go back to the same place where it started. And I'm going to explain in the latter half of this talk why that matters so much. But for the time being, let's just take it as probably the most important property of these devices. We also want them to have a large conductance range. So we want to, have a range of say 10x between the minimum and maximum conductances. And we want to cover that range through many incremental changes. So we don't want to just apply a pulse and boom, it's on the from lowest to highest. No, we want it to be gradual and nicely. So if you look at what is the most advanced devices, at least for this application, we see phase change memory type devices, these PCM devices that rely on reversible phase transitions in chalcogenide glasses. So, but if you look at the modulation graph that I'm showing just beneath it, is okay, the increment side at least is smooth, right? Gradually rises. It's not linear, but as I said, it's okay. But then when you want to decrease the conductance, it's instant, it's abrupt, it's utterly asymmetric, right? And this extreme level of asymmetry basically render these devices completely unsuitable for analog deep learning applications. A competing technology to PCM is filamentary RRM, which is the one that you're seeing next to it. And while these devices are also asymmetric, I mean, at least they are significantly better than PCM. So that's the start. But the biggest problem, I would say, is that these devices have very low yield. So when you make hopefully same devices, they end up being very different. So they have a high device-to-device variability. And that is actually something inherent to these devices because those conducting paths that form in those filaments, which is the conducting path inside this insulating matrix, they form in random locations. So you can't control really during fabrication or post-fabrication while using where these are going to be formed. So in the end, devices end up being quite unreliable. In contrast to these filamentary devices, magnetic and ferroelectric devices are very reliable. They have very low device variability, high yield, so far so good. But the problem is achieving more than a few states, even more than two states with these devices is very challenging, because the physics that are feeding these devices happen extremely fast to a fault. So controlling it, taming it such that we can tune it gradually is very, very, very challenging. And actually, if you stop here for a second and look at all the three technologies that I showed here so far, and all the ones, I mean, so many ones that I didn't, and that assumes that at least you know the field. These are all devices developed for memory applications, right? These are devices that were designed for storing information. But instead, now, what we want to do is actually process information. We don't want to store information, we want to process it. So, learning, by definition, is to tune the variables to the optimal value via many, 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 many incremental modifications, right? So, we don't want to store it, we want to process it, and therefore we need to optimize the devices for state transition properties rather than just state preservation properties. And that is exactly where the non-filamentary ionic devices, which are shown on the rightmost side, come into picture. And an easy way to understand what these devices do at a high level is, imagine you have a semiconductor that you can control the dopants that exist in the semiconductor through electrical pulsing. So normally with transistors, we dope the semiconductor in the foundry, package it, send it out, and then it is what it is. You can move those dopants inside, or electrons, actually, not the dopants, move the electrons that come from inside by using electrical voltages. But now, what we want to have, and what we do have with these non-filamentary ionic devices, is you have the semiconductor material, and you can control the amount of dopants that exist in it post-fabrication during the operation of it by applying electrical pulses. So in slide 12, on the left, you can see at least a magnified version of the same picture that shows that these devices comprise three key layers: a reservoir that contains essentially an infinite number of ions ready to be released upon the application of an electrical pulse, an electrolyte that conducts these ions, again, when there is a, electrical potential, while strictly insulating any electronic leakage through it. And finally, an active layer, which is our semiconductor in this case. In most cases, it's a transition metal oxide, which has a controllable conductivity depending on how many dopants are inserted or taken out from this material. So actually, if you use lithium as these dopants or these ions, what you end up having is pretty much identical to a solid state battery, right? And thanks to the very advanced battery literature we had, and many lithionic devices, that lithionic materials we know, there have been so many successful applications using lithium. But the key problem is lithium is a CMOS incompatible material. What that means is you cannot build these devices in silicon fabrication. So the idea normally would be to have a front end technology comprising conventional CMOS, and then on the back end you would build these devices such that the chip is complete. But if you use lithium, you cannot integrate these devices to the front end silicon, because again, none of the foundries would allow you to introduce lithium to their processes. It's a very, very tough to work with contaminant. So that's why people started looking into oxygen-based devices, right? At least there are so many oxide materials that are CMOS compatible, so that checks that box. But the problem with oxygen is it's a large ion and it's also heavy. So whenever you try to move it around, A, it's not going to be fast, B, it's not going to be energy efficient, and C, if you do this back and forth so many times, given oxygen is large, host lattices will actually be mechanically degraded because you are trying to insert and extract something quite big, and after many cycles, materials start degrading. So that's why finally the focus shifted into hydrogen-based devices or protonic devices, because we are talking about ions, so it's just a proton. And it's a good idea because hydrogen is smallest ion. So proton, sorry, is the smallest ion and it's lightest ion. But the absence of any protonic solid state material critically limited the applicability of these devices by means of integration and scaling. You couldn't basically use conventional methods to build these devices. So early demonstrations actually used some liquid electrolytes or polymeric electrolytes, neither of which are particularly compatible with silicon fabrication. So you can't use either one of them to make small devices again using CMOS silicon nanofabrication techniques. So a key innovation we had in our lab over the last 3 years was to come up with a CMOS compatible solid state protonic electrolyte, which is phosphosilicate glass. So this phosphosilicate glass, or PSG for short, is essentially silicon dioxide. And this is pretty interesting because people have been looking into materials that with exotic ceramic materials that comprise elements that at least I haven't heard of before, and I'm sure the in the depths of periodic table there's so many elements it turns out, and there are a lot of exotic choices. And don't get me wrong, some of them work excellent in many applications, but what we chose to use was silicon dioxide, essentially, by far the most well-known oxide, I guess, to humankind. And what we just did was to dope it with some phosphorus at a very particular level. The good thing about it is PSG already exists in silicon fab, so it's certainly a compatible material, and it's a very well-known material. So most properties were studied, so we could tweak it in the way that we wanted to. The good thing about this material is that it has a high proton conductivity at room temperature, and it does it without relying on environmental humidity, which is important because some ceramics actually work to absorbing water from environment, but not PSG. PSG has some intrinsic properties that allows it to conduct protons, at least the PSG that we use. And it's also a good electronic insulator, which is again important, such that you have an electrolyte. And it also has a high breakdown field, which is a very confusing thing for many. I mean, even if you are within the field or outside the field, because breakdown field is definitely not a parameter that is cited when you're trying to build an electrolyte. But in order to understand why I'm mentioning that here, why on earth it matters at all, we need to actually understand how protons move in solids, right? As electrical engineers, we know how electrons move quite well, but how protons move is very different with respect to how electrons move. So protons actually move in solids through a series of hopping motions, and each hopping event has an energy barrier similar to the one that is shown in blue in the curve that is on the bottom side of slide 12. So imagine that this proton is at the bottom of that energy landscape, and in order to move, it needs to overcome this energy barrier such that it can hop into the next one and then do it again to hop into the next one. And these energy barriers are high, even for the PSG, which has a relatively low energy barrier. These are high. For example, in PSG's case, it's zero.4 eV, which is much higher than the thermal excitation that you will have at room temperature, which is 26 milli eV kT. So traditionally, it's not going to surprise any one of you to hear that ionic devices were not fast. The state of the art when I started this project with these ionic devices was a millisecond range. And milliseconds is definitely not the time scale that you want to be related to it when you want to do compute applications, right? We are our whole our processes are in gigahertz and above. So we're definitely talking about much faster than milliseconds. We don't want milliseconds, too slow. So in order to change this though, if you start applying an electric field onto this device, you start tilting the energy landscape. And as you increase and increase and increase the electric field that you apply, you can tilt the landscape to the point at which that you don't have a barrier anymore, right? So that is what you're seeing with the purple curve that is on top of the blue one, again in slide 12, that there is a point at which the barrier ceases to exist in the direction of motion that you want to push the protons. So in other words, in technical terms, this is now granting you ballistic motion for proton transport in solids. And indeed, most materials, whenever you try to apply this level of electric fields, which 10 megawatts per centimeter in electrical engineering units, or 1 volt per nanometer in material science units, which I never understood why they chose to use different ones, but it is the way it is. Whenever you do that, most materials will just simply turn into ash. It's as simple as that. So the materials that you use would degrade beyond use anymore, and then they would be dead. But instead, PSG can withstand these electrical pulses, very high electrical field pulses. And to demonstrate that, in slide 13, you see the devices that we made at the nanoscale. So these devices were at 30 nanometer node. I fabricated them at the clean rooms of MIT. And when we tested these devices, we saw state-of-the-art combined properties for any device technology that was presented for analog deep learning applications. So first of all, these devices are fast, very, very fast. So to put that into context, we were able to program these devices using only 5 nanosecond pulses, whereas as I said before, the previous state-of-the-art was in milliseconds. So these are 1,000,000 times faster than the previous state-of-the-art, which is highly rewarding because it doesn't happen all that often. So to improve the previous state-of-the-art by a factor of 1,000,000. And not only that, each 5 nanosecond pulse, only contains 2.5 femtojoules of energy, which is extremely low. And also note here that almost all of this energy, this 2.5 femtojoule, is actually the capacitive loss that goes to doing charging and discharging of these devices. The actual energy that is associated with moving the protons inside this device is only 15 attojoules, which is an amazingly small number. And from the middle graph in slide 13, you can see that this modulation curve that we are seeing here is pretty much the same as what I showed for an ideal device, right? It is nearly linear, it's highly symmetric. The conductance range is quite large, it's 20x, and we are covering this range using 1000 pulses. And in slide 14, to continue on those, we have good retention, so good non-volatility, and we also have very good endurance. So you can see there in 1,000,000 pulses, the device at least did go through any change. And some might ask, why did I stop at 1,000,000? Because I also wanted to see how the retention works. So 1,000,000 pulses essentially, although the pulse itself is only 5 nanoseconds, so 1,000,000 of them doesn't take any time at all, I also need to read them for some time to see if the change was indeed non-volatile. So then it becomes actually 1 second each, and 1,000,000 seconds is already long, and I wanted to graduate at some point. So that's why we stopped at 1,000,000. But even then, afterwards, we continued pulsing these devices. So far, we haven't seen a degradation even at much higher numbers. But a full-on study needs to be done, obviously, for endurance in detail. And on the right side of slide 14, you can see that in real time this time, what happens immediately after when the pulse is there. Because it is possible that you apply the pulse and the change actually happens over a certain duration of time. What is happening instead here, as you can see, particularly on the inset of the right, we send the pulse and the change is pretty much instant. Oh, in technical terms, it's sub-microseconds. That's what we can claim because that was the limitations of our measurement setup. But at least it is very very fast, and it's not happening through a slow and elongated equilibration, which is pretty good. So slide 15 is actually a bit of a plug more than anything, but it has been a really great pleasure of mine to share that over the last month and a half by now, since the results became public, we received quite a bit of press interest, which is quite nice, and we are now moving forward with the devices into the higher levels, such as arrays, and then to system level studies. And while this slide is going to conclude the device part of this talk, as I was mentioning second ago, the complete job is actually far from done, right? Because these are unit devices, then you need to array them, then you need to build the peripheral circuitry, and ultimately run algorithms on top to actually go to the deep learning applications, because that's what we're after at the end of the day. And obviously, you need unit devices, but it's not enough. So today, I'm not going to talk too much about architectures. I can if there is interest in the Q&A maybe, but I'm going to focus on the algorithm side of it. So if you go on slide 16, the idea here is at the end of the day, we want to train a neural network, right? So what we have to ensure is that the changes we exert on these resistive devices, they need to correspond to accurately training a neural network. Because if they don't, then what's the point? So, and for this task, many people assumed that, oh, okay, we have training algorithms that we designed for digital applications, most famously stochastic gradient descent. I think it was originally designed in somewhere in 1800s by Cauchy. I might be wrong, but that's what I recall. There is a French original paper. And since it helped so much to us over pretty much all of deep learning, many variants of stochastic gradient descent, people thought, okay, why not use it here too? It has served us so well, they're probably going to work here too. But the thing is, analog architectures have some non-idealities at this device and circuit level that simply doesn't exist for digital architectures, and therefore we now need to update the algorithm such that they can become tolerant to those non-idealities. And the way to test the effects of these non-idealities on actually training a neural network, we rely on simulations. So what we do is we pick a network, say convolutional neural network, recursive neural network, fully connected, doesn't matter. We pick one and we simulate, we model, first of all, we model the device and the circuit and the non-idealities associated with them. And ultimately we simulate the training to see what is the resulting accuracy and if there was any degradation. So that's what we do. To show an example, let's move on to slide 17. And on the left, what you are seeing is the training of an LSTM type neural network using stochastic gradient descent, our beloved algorithm, on 3 different models of devices of increasing asymmetry from blue to green. And for those who are not familiar with LSTM, what it's trying to do is, first of all, it's trained on the War and Peace novel of Tolstoy. That's the data set it uses. And what's trying to do is to guess the next character in the string. So you can imagine it as an autocomplete of sorts, although how they work are completely different. But that is what it is trying to do. It is not an image classification network, but it is text processing, or hopefully, evolved versions of this does language processing ultimately. So what you're seeing here, and also, by the way, just one last note, in the graph, the y-axis is cross entropy, which means the error. So the higher up a value is, that means the network is performing worse. The lower it is, you have less error, and it's a logarithmic scale. So actually, a little bit, even a little bit of a change in y-axis means actually quite a bit of change. Okay, so now when we look at this graph, what we see is, with respect to the black curve baseline for a perfectly symmetric device, these ideal devices that I mentioned a while ago, all of these asymmetric devices cause a very heavy loss of accuracy, right? And even for the blue curve, which looks pretty symmetric to the naked eye, I would say, but it does have some little amount of asymmetry. Even that has a significant loss of accuracy. So this is a problem, obviously, and given that most devices that exist in the field are mostly resembling the green one and maybe sometimes the red ones, people knew this problem. People have seen this in their own simulations, and even in some mini demonstrations some people did. It was actually the possibly the most well-known problem of analog processes for a long while. And therefore, there have been some solutions, right? Some mitigation techniques proposed by the community to say, okay, how do we get around this? How do we beat the problem of asymmetry? Unfortunately, most of these proposals lie on one of the two main categories, and some rare occasions, even both of them. So, first group says, why don't we use a feedback loop around each update? So, we do an update, and if it is asymmetric, we can compensate for it. We just check it, check if the update was the one that we wanted to, and then if it's not, let's correct for it. And from the description I just gave here, you can see that this is a serial operation. So because you need to basically check every single update, see if it is right, and it's actually a repeated serial operation because you need to compensate for it, maybe a few times even, because you do the compensation, maybe the compensation is not enough, so you read it again and compensate enough, so on and so forth. And as a result of that, it sacrifices the very parallelism that lies in the core of these architectures, right? That was the point of them. So if you choose to do that, maybe you will fix asymmetry, but you will actually have an AI decelerator, which is definitely not something that we need at all, right? So sacrificing parallelism is definitely not the way to go. An alternative idea we could do, people proposed, okay, let's build a circuit around each device such that the circuit is, which is called a compliance circuitry, by the way. The circuit forces the device to act in a way that we want to. And okay, again, this might solve the asymmetry, but this goes back to the problem that I mentioned for GPUs, right? The hundreds of transistors per core. Well, now we're going back to that. We have a device, now we have many transistors around it that are forcing it to do something that just the way that we want to, hopefully. And in the end, this application, this method, if you use that, you completely sacrifice the area and energy efficiency that are associated with these architectures. So again, beats the purpose. And possibly the most interesting thing, actually, about this problem is, even though this was the most well-known problem in analog deep learning, no one actually knew why that was a problem. So, for example, noise, we knew noise existed, we knew noise was a problem to a certain extent, and we understood why noise was a problem. It made sense. Asymmetry, everyone knew it was a problem, but no one really knew why. What were the theoretical underpinnings of this problem? Why was it happening? Why can't we get rid of it, right? And to explain how it works, I'm going to show you slide 18, uh, which is basically the simplest learning example that you can have, a single parameter regression. So what we're going to do is that you are seeing the graph on the very left, and that is our data set. And what we will try to do is to find the mean, the average of the data set. It's not going to get any simpler than this, right? It's the simplest learning example you can have, single parameter regression. And as you can see from this data set, it has some standard deviation, which is this red band. And it has an average value, which we are going to call G naught. And the naming convention will become more apparent as I move towards this slide. And again, as I said, we will try to find the average of this data set. That's our task. So on the top row in the middle, we will try stochastic gradient descent, our beloved algorithm, to train to train the ideal device that is just next to it in this application. And nothing interesting will happen, right? We will start at a random initial point. I'm talking about the top right plot now, SGD using the ideal device. We'll start on an arbitrary point, and as training continues, we will converge to this average value, G naught. Nothing interesting, really. It's what it's supposed to happen, and it happens as it's supposed to. So the only thing in here to note is the inset in the top right graph, that even when we see convergence happening, what is actually happening is the value doesn't stay there in a static fashion, but instead it moves in the vicinity of the optimum value. So, which makes sense because some of the values will be above the mean, some of the values will be below the mean, right? And if it is above, it's going to go a little bit up to take that into account, and vice versa if it is lower. On average, everything will cancel each other out, which is basically the definition of the mean, and it will stay there. And that's exactly what's happening. And therefore, this G naught value is not a static point, but instead it's a dynamic equilibrium from the data sets or algorithms point of view. So now if you look at what happens for an asymmetric device, and on the bottom just beneath the ideal devices graph, you can see the modulation characteristics for an asymmetric device. And as I said, the way to understand these devices is you do an increment and you do a decrement, and they just don't cancel one another, right? But in particular, if you are above this orange line in the middle, you do an increment which is saturating, so it's tiny, and then you do a decrement which is sharp. You will have a net negative, right? And if you're below this orange line, the opposite will happen. So actually, whenever you do an update and whenever you change the conductance, you pick up a term that shows the direction towards this orange line in the middle. And what's special about this orange line is it is the only point where the incremental change is equal in magnitude to a decremental change, which is why we often call this G symmetry, the conductance value that the device is symmetric, the only conductance value actually where the device is symmetric. And if you think about it, this is the value where the conductance wants to remain at, right? This, whenever you change, it wants to go to there. So that's why we can actually call this point as the dynamic equilibrium of the devices from devices perspective. And as a result, if you try to now train these asymmetric devices with stochastic gradient descent, what you will have is, instead of converging to the optimum value in the green line, you will converge somewhere in between the optimum value and the symmetry point. And as a result, it will essentially fail because that's not what we want to have, right? And to even think of a total experiment, even if you were to start from this optimum value, say that you were super lucky, you guessed the answer from the beginning, what you will end up is you will still go and converge to this point, because we know from the top right, when you're at the convergence, when you're at the optimum value, you get pulses that are randomly up, not randomly, but half of them are up, half of them are down, on average zero. But we do know from the study that we just carried out for this asymmetric device that drives you to the symmetry point, right? So even if you start from the green line, as training continues, you're actually going to go back to this converged point that is in between the G naught and G symmetry. So it is a pretty fundamental problem, right? Even because if you can't even stay at the answer, how are you going to find the answer, right? So it's a big problem. So in slide 19, I try to put this in a more formal setting, relatively speaking. So on the left, if you continue understanding what stochastic gradient descent is doing, is it has an area function, right? And it tries to minimize this area function. That's what all optimization problems try to do at the end of the day. And we can imagine this the area function or the energy associated with it as a potential energy, right? That's what we are trying to minimize, the potential energy, and when we do it, we will be happy because that will be the answer that fits our data, whether it's a single parameter regression or whether it's a massively advanced neural network. That's the key idea philosophically. But what we are seeing actually in an analog architecture, whenever you change the conductance, so whenever you move, you actually pick up another energy. You pick up another force related to that energy as well. And since it is associated with change or movement, it is more like a kinetic energy, right? And what stochastic gradient descent is doing is it tries to optimize the potential energy, but actually samples the total energy. So it ends up converging to the wrong optimum. It still converges. It's not divergence, right? You saw in slide 18 before, it did converge to a point, but it is just not the point that we want it to. That's not a point that we care about. So if it was a neural network, that would mean that it's a network with a high error, because that's not doing what we want it to do. It's doing something else, something completely else. So in order to fix that, what we ended up having to do was to come up with a new algorithm. It is basically a modified version of stochastic gradient descent, and the key idea is to separate these competing equilibria into two subsystems, where one subsystem, the auxiliary one, can minimize the kinetic energy such that the main subsystem, the core subsystem, will be able to accurately minimize the potential energy. So since we are now trying to minimize both energies together and incorporate that into the algorithm, we name this algorithm as stochastic Hamiltonian descent to refer that it is doing the total energy, right? It's minimizing the total energy. And as a result of that, it converges to the right optimum. So I am not going to show you the pseudocodes or the steps that takes this algorithm, because that's definitely not that doesn't sound like a good talk to start with, and it's extremely complicated to follow the steps of an algorithm, particularly when you're seeing it for the first time, even if you live and breathe algorithms. So but instead, in slide 20, what I'm going to show is the result. So on the right now, the right plot, you can see the same LSTM example trained for the same device models for stochastic Hamiltonian descent. And immediately you can see that the loss of accuracy is now mitigated, right? Which is great news. Even for the highly asymmetric green device, the accuracy penalty that we are paying is almost gone. But what is most exciting, actually, in this slide, and to be fair, in a slide that I give live, this comes in animation, so it's even more apparent. When you try to train devices that I showed in the earlier half, the protonic devices that are behaving so nicely and already quite symmetric, it ends up beating stochastic gradient descent with perfectly symmetric devices. So these devices that don't exist, these hypothetical ideal devices with the most conventional algorithm, they actually lose to the devices that are new here, the protonic devices, in combination with this new algorithm. And this is extremely exciting because analog hardware has always been proposed for speed and power reasons, right? It was faster and it was more energy efficient, but never more accurate. Actually, that was the problem. People would withstand the inaccurate nature of analog processes just for the sake of getting the power and speed benefits. But now what we are showing here is that if you actually design the algorithm cognizant of the features of the devices, you can beat the conventional algorithm. So it actually opens up possibilities. In other words, what we are doing is we are transforming this bug of this analog device, asymmetry, even at low level asymmetry at least, into a future that it uses such that it can converge faster and possibly provide better generalization performance, which is an incredibly important metric for neural networks. And finally, I also want to note that there are more applications to analog processes beyond deep learning, primary of which is the generalized machine learning, and more specifically, randomized numerical algorithms such as quasi-Newton or eigenvector decomposition, matrix sketching, streaming, so on and so forth, wherever you want to do heavy loads of linear algebra, particularly if those are rank 1 updates, these architectures can provide quite a lot of benefits. And in slide 21, I want to show the main question that we are left with. How do we innovate faster? And again, as there are no animations, you already see the spoiler down beneath it. But what we need to do is we need to let go of this linear progression that I have used as the banner on the top, right? The idea of oh, okay, someone will make devices, then those will give it to the architecture folk, and architecture people will build the system, and then they give it to the software people, and then the software people will run out. Just doesn't work. This doesn't work because we don't know when we bring devices into systems level or systems into algorithms what is going to happen. We don't know how they will interact. So actually, this works for silicon, by the way, for CMOS, for digital. It works because we have extensive experience in building silicon CMOS systems. It hasn't always been this case, but now we know. After so many years, so many decades, we know. But when you prematurely try to compartmentalize this field into devices, architectures, algorithms, it doesn't work. We need to do co-optimization. We need to rethink this entire concept as a whole, and we need to optimize it together. So that is what you see in slide 22. We actually need to adopt a cyclical fashion in order to uh, get to these devices. So you need to build optimal devices, obviously. You need to build efficient architectures with them, and you need to make analog specific algorithms. And the cycle basically means that whoever makes the devices will have an idea at algorithm level what will happen, and also whoever is building the writing the algorithms will know what features of devices they need to live with and what features they can exploit. And when it is in a co-optimization form, these processes can become a reality pretty soon. And don't get me wrong, this is not an easy job that I'm describing here, right? So this is going to take all the disciplines from applied mathematics to applied physics and all the engineering disciplines you can think of that lies in between the two. But given that the potential benefits we are trying to get are so high, the urgency is very much there, if you remember from the introduction part. And the progress itself is very promising. It's probably the most one of the most easy, one of the easiest fields to justify to be working in. And finally, I mean, it has been a real pleasure of mine to give this talk today. Thanks a lot to Katerina for reaching out. And I'd be happy to answer any questions and happy to get into details and so on as you wish. So thanks a lot.
Thank you, Murat. This was an amazing talk and so fascinating and so impressive. So, congratulations again. And it's so genius how you increase the speed by such a high number that you and that you don't lose basically you don't damage, and it's at room temperature, so it's all the important problems that not all but most important problems we had you managed to solve so elegantly. So congratulations again.
Thank you.
And and I have a question that is a little bit related to a room we had last week, also on Friday. I don't know if you know Mike Levine or Levin was here from Tufts, and what he does is develop these xenobots that kind of can self-replicate and also solve problems and self-assemble and stuff like that. And he also then works with cognition and tries to solve the problem of that kind of behavior is performed out of many units, and that these many units at some point develop an individuality, like
Mhm.
of processing. So I know it's probably totally far-fetched. What you said, you conserve basically that there's parallel processing. So what do you think is each parallel processing basically? Does it represent these units like in organisms? And do you think that your material can achieve this higher cognition and, like, you know, integrity of processing, that it can develop like an AGI or a general cognition that would be more generalized? Because a few factors are theorized to be a higher speed and a high connectivity, and that you have different parallel units basically represented in a system.
Yeah, no, this is a very good question, and I hope. I mean, I will give an answer, and if it turns out I understood it wrong, please correct, and I would be happy to give, re-understand it, try to re-understand it. But I think in whatever application that you are looking for, whether you are making self-assembled systems or self-healing systems or computing systems or anything, any engineering challenge that you can look for, I think the key idea is that are you working with the fundamental physics or fundamental dynamics or fundamental mathematics, can whichever makes the most sense. Do they work for what you are trying to achieve? So let's try to break this down into a few steps. So what we have today, right, with digital architectures is these binary systems, and the reason we like them is it is easy to do binary logic. It has some advantages, and for some key algorithms such as sorting and whatnot, the binary works fantastically. These ones and zeros work fantastically. So what did we do was to optimize transistors, and transistors, the physics that are behind them, particularly CMOS or MOSFETs, is that they can be on and off, and they can be switched back and forth fast in a nice manner. So on and off, and mapping that to one and zero, basically the physics of the transistor, the intrinsic physics of a transistor lends them very nicely to binary operations. Now, then we can make a similar analogy in quantum, right? Quantum computers are meant to process everything in a way that classical computers doesn't. So what they do, in some sense, is I'm not going to use the word parallel because that would be wrong, but they process things in a superposed way. And the reason they can do that is the underlying physics of how qubits interact with one another is essentially allowing them through entanglement and superposition that these quantum computers can achieve what they do. Theoretically speaking, classical computers can do what quantum computers can do too, and vice versa. It just would take maybe infinite time, infinite money, infinite power. Then, even if it's not infinite, it is very, very large, right? So the key idea we are seeing, even with these two systems, is the physics that you have the right one for the application you want to do. For when we bring this analogy now towards the realm of deep learning, we do know what operation we want to do. We want to do a lot of matrix algebra, right? And it turns out that there are some devices that, again, physically speaking, uh, they lend themselves to matrix algebra in a nice way. And whenever you have that kind of alignment, that is where you get the most efficiency. So one way of looking at that is you can always, I think, build overcomplicated systems with a building block that doesn't really naturally belong to there. But this overhead that you are going to pay is going to make you either slower or more power hungry. So that is, I think, the key philosophy behind these analog architectures. And in actually, I'm quite sure in many disciplines, whenever some people come up with much higher efficiencies or much faster devices, that is what it almost always is. If you have the materials, if you have the physics, if you have the mathematics, or if you have the system interactions that are naturally doing what they want to do is the same as what you want them to do. Whenever that is the case, you get the benefits. I think that is what probably what you must have heard in the Professor Levin's talk. Although I wasn't familiar with what they were doing, I just checked them out, and I am seeing. I think they probably would agree that this is at least partially applying to them as well. But that is the key. You need to have a very deep understanding of what is it that you want to do, and then you need to search for what would do it naturally instead of forcing what exists into what you just want to do. You will probably get it doing, right? Like, I mean, GPUs do a relatively decent job in deep learning, but ultimately, if you want to do more and more and more complex operations of the same type, you need to abandon them and then find a domain that these operations can be handled intrinsically and more efficiently.
Yeah, thank you for answering that. And please raise your hand if you have questions. Joyce, Dennis, Abyss, if you have a question, please flash your microphone or just go ahead.
Go ahead, Abbas.
Thanks, Denise. Hi, Kat. Hi, Joyce. Thanks, Maura. I was present for the most part of the presentation. It's really, really impressive work, and I'm really fascinated as to like how um, analog computation is actually willing to propel the deep learning, or at least like the machine learning, deep learning um, architecture that's been widely adapted by the digital. So that being said, I do have a couple of questions for you. The first one is, um, what are the specific thermodynamic conditions that these analog devices need to be placed in? Of course, like you mentioned that your system that you developed actually works at room temperature, but you also mentioned some materials like silicon dioxide, which typically is used like a piezoelectric material that actually responds with some kind of pressure or like like I said, thermodynamic conditions. So I'm just wondering how you can reliably implement these kind of devices given the variation of, or at least like the thermodynamic variation that they're placed in. So I'll start with that one.
Hmm. So I mean, it's a good question. The silicon dioxide can indeed be piezoelectric. The one that we have doesn't satisfy the conditions for it to be piezoelectric, at least, I know that's not what you specifically asked. I think that was more of an example of possible issues with it. But so the material that we are depositing, we use plasma enhanced chemical vapor deposition, and the technique and the getting the same material again and again is relatively well established, I would say. So since it is a very familiar material to silicon processing, there is an extensive literature of getting whichever PSG is that you want to get to in a reliable manner. So from that point, from the fabrication point of view, getting it the same time, same every time, is again relatively straightforward. It is not any different than what we are commonly doing for silicon processing for all the transistors we have, right? So there obviously will be some variability, but it is well beneath the levels that we can tolerate. The second part of it is how does it, what thermodynamic features it needs, and also I guess a part of the question could be, does the thermal changes affect the operation of the device, right? So the devices that we built are working in room temperature. Theoretically speaking, they can work at lower temperatures as well, because as I was mentioning with the what the field is doing, it removes the barrier. So you don't really need KT anymore. You don't care about it. And actually lowering the temperature, if you can afford the cooling power, which is a question mark of its own, but it would lower the noise. So it can actually be beneficial to lower the noise. Then you would probably spend either less time in the ADCs to integrate, sorry, in the op amps to integrate, or you can use lower power analog digital interfacing. So it can actually come with some advantages. As the temperatures go high, um, the we don't anticipate any change. We have at least tried these devices up to uh, 50, 60, 70 Celsius, and the devices seemed operational, but a detailed study of, oh, is it the exact same, hasn't been done yet. And whenever you build a processor, of course, the temperature increases are an important property. Whenever you design transistors also, you want it to operate the same within a temperature window. But one good thing, at least, about these devices, given that how energy efficient they are, at local temperature increases not that expected. I mean, it's going to be far better than silicon. So you can cram in many more devices before heating the chip by any meaningful temperature. For example, we estimated how much the chip would heat when it was. We assume the chip first of all. We have unit devices, but just to walk you through the estimations we had, We assume this chip is utilized fully, so it is used at the highest power that it can take, and we anticipate it's only going to increase by 2 Celsius. And the change of 2 Celsius is almost impossible to affect anything, I would say, like 20 to 22 Celsius, or 30 to 32, it doesn't really matter. But so we are not really that concerned about the thermodynamic changes. I mean, at the end of the day, these devices will be encapsulated once and packaged for a chip form, and maybe if need be, they might be coming with their own cooling apparatus itself, similar to many, like a fan, for example, that you have in a computer. But yeah, I would say that we are not strictly relying on certain thermodynamics or certain pressure, like environmental or physical changes to work, but instead we only rely on electrical changes. So that helps with the reliability significantly, as well as using a material that is quite well known.
Right. Thanks for that. My question was also trying to address the different packaging considerations that you have to make, um, given that how certain thermodynamic conditions can affect the computation. But yeah, you answered it really nicely. My second question is, how versatile are these analog devices? Versatility in a sense that how can they address sort of like this ever evolving algorithms or deep learning algorithms that have been devised in recent years that seem to kind of overwhelm the existing ones. And if you heard about transformer models, diffusion models, these are now becoming like a trendy thing. So I'm just wondering how the hardware is able to kind of address or sort of like utilize these methods to essentially sort of expedite the precision making process. The prediction making process, right?
Mhm. That's an excellent question, actually. Because the reason I say that, and I'm not saying it as a cliche. It's actually really a perfect question. There are so many applications that we want to address, and there are also some chips that can only address a subsection of them. So whenever you talk about commercialization, for example, of this technology to become real and hit the industry and actually remedy the problems of AI hardware, absence of AI hardware, you have to have a general purpose chip. You just have to. There are some, for example, some implementations such as spiking neural networks. They can do some things, but not many things, and that subset is not enough to justify sometimes to justify the development cost necessary to bring those devices or mini systems to full scale systems. So these architectures that I showed you about today, the intrinsic processes, these resistive crossbar arrays, you can train, at least so far, from the ones that I know, any type of neural network. For example, we have tried on simulations, fully connected neural networks, all the way to actually restricted Boltzmann machines, to be fair. Not that they are extremely relevant, but convolutional neural networks, LSTM type networks, there are recursive convolutional neural networks as well, the combination of the two. We started looking at them more recently. And for example, diffusion models that you said earlier, they should be all possible. There are only very few things that they can't do. For example, if the algorithm that you have relies on a momentum method, it's not going to happen. The reason for that is the parallel updating of these devices actually is interesting in the sense that when you do the outer product, the user doesn't actually get to learn what is the outer product that is applied. So you send these vectors, you translate into them into pulses, and then these pulses are fed into the crossbar, and the update just happens without user knowing what update was done. So if you really want to know, you need to read it before and after, which is you don't need to for a non-momentum type algorithm. But if you insist on knowing what update is done, you actually need to do read before and after. Again, something not what we are really looking for. And again, the reason for that is you are actually updating the network implicitly. The update matrix is hidden from the knowledge of the user. So The only thing that I know that they cannot do is momentum-based algorithms and some adaptations of that, right? Like there are so many approaches that are adjacent to momentum that relies on knowing the previous updates or recent history of the updates. And I mean, if you really insist, you can do it as again, but then you will start sacrificing from the performance. That's why I mean that you can't do them. It is not really a fundamental inability, but it is a practical inability. But other than that, all types of neural networks, you should be able to map them into these. If, for example, the matrix size is larger than your array size, you can patch multiple arrays, or other way around. If you have small convolutional kernels that you want to map onto a single array, you can divide the array into multiple pieces. We have demonstrated some of those early on. So these are pretty flexible. And one last thing to basically tie this up is uh, another question would be, for example, how do you do the activation and error functions, right? Do you want to do them in analog, or do you want to actually do them in digital? And people ask this to me quite often. Why do you go between analog to digital this frequently? Why can't you just get rid of the digital altogether? You can build an analog nonlinear function processor, which we can, and you can also even attach senses as the input rather than a memory data set, such that it does real-time learning, which is a very cool idea, and we can indeed do that. It's possible, but you will basically trade flexibility for application specific. So I mean, it is very common idea, right? You trade in general performance to application specific performance, and in some cases it makes perfect sense. But what I think that the first place that these architectures need to come into is a general purpose AI training. And if these processes will actually have a business impact at the front end, at the users end, software end, people should be able to use the exact same language packages and exact same models on these architectures seamlessly. The transition, basically, you take a rack off, take this rack on, and the only thing that you will realize is that it is just faster. Other than that, there shouldn't be no complications, even if the algorithms are a bit different, as I showed, SGD to SHD. Though that the philosophy of that change can be applied to many optimization algorithms, we just applied it to an SGD, given that it's the most common one. But other than that, they are most certainly versatile, and they can address many different types of neural networks, as far as we know, at least so far.
Yeah, thank you for that. And I'm also like really excited that you mentioned something about not using stochastic gradient descent, but it's stochastic Hamiltonian descent that can outperform in your specific architecture. So looking forward to new updates and like I said, really exciting field. So thank you for answering my questions. Mike, over to you, Kat.
Yeah, there were questions in the chat. Bobby had the question: what is the throughput writing and reading of the weights? You answered it, but if you could,
Yeah, I can repeat it. So actually, the throughput is easy to compute for these architectures. So you need to first define how big is your array, a unit array. Let's say it's n by n, a square one, because why not? And then the array does fully parallel multiply accumulate, right? So when you use the array, you use 2 times n squared operations. You do 2 times n squared operations, because n squared multiplications and n squared additions, right? So we often use 4,000 for the n. So the basically we are doing 4,000 squared times 2 operations, and all of this happens within the time of an integration time, which is limited by the noise, how much noise you have, how much noise you can afford to have. And that number is usually around 80 nanoseconds. And then if you basically do the math, it becomes 400 tera operations per second for these numbers that I gave to you. If you can lower the noise such that you can cut the integration time less, or find a way to lower the line resistances such that you can make a bigger array, these numbers can increase. But even with these values that I said, it's just 400 tops should be achievable for the throughput.
Yeah, thank you. Denise, do you have the question?
Salam Murad Hojam. That was a really interesting presentation. Really, there's a couple things that went over my head, so I'm just going to ask a very basic question, which is, what do you see as the future of this work? What would you like to work on next?
Yeah, so the I'm basically now trying to spin off a company to follow on this into the commercialization route, because I think the timing is right, most importantly, because the research side of it is advanced enough to take on a development challenge. So the next stages would definitely be building more. First of all, transitioning this process into a conventional facility instead of me doing them in a clean room. Foundry probably should get involved, such that we can do much higher volume processing, and then studying the system details, as well as working the front end, such that as I said earlier, the different language packages that already exist can be used to run on these processes as well. So the future directions I see is definitely scaling these things up. The other than that, from a scientific point of view, there are some actually interesting domains which I don't know if it's going to be me who pursues them, but this material and this high field, high speed operation regime actually can be used in adjacent fields such as electrochromism, the smart windows, artificial photosynthesis, and micro batteries, right? And basically in any field where you need fast ion transport. And there are some very exciting opportunities there for academia to work more on, and to see what this material now enables. PSG is a known material to silicon, but not necessarily a known material to the field of ionics, I would say. But I think they started appreciating what it can do and then what it brings. So I am quite sure we will see PSG more and more in ionic device, other types of ionic devices, as well as the computing ones that I'm working on.
And last question: do you see? Are you employing automation in the physical processes, or do you see room for that?
Automation for production, you
Yes.
mean? No, currently not. I mean, the the way these devices are made is basically a grad student who was myself going into a clean room and doing steps one by one. It is not automated by any shot. I mean, some of the tools that we use are semi-automated, but that's about it. Obviously, at the production level, these would be automated in a clean room, such as, I don't know, say TSMC's clean rooms. A wafer would be processed step to step in a fully automated manner, but not now. Hopefully, in the near future.
That's exactly why I was asking. So, like, wow, it must be. I've seen clean room procedures. It's very time consuming. It would be very, really help you to get some robots to do this stuff for you.
Yeah, absolutely. No, fully agree. I mean, the when you are talking about making billions of these devices, it is not feasible to employ more and more grad students to do that, I would say. Hopefully, the foundry transfer should go smooth, and then they can make 8-inch wafer scale devices. Then the number of devices that comes out of the foundries way far beyond than what a person can. So, but yeah, we are just simply not there yet. But definitely, the direction is that way.
Right on. Thank you so much.
Thank you.
I have a quick question. I'm also not in this field, so this is more of a broad kind of a question. Just what problems that this would be used to solve excite you most in the near term and the far term? Thanks. I'm
Mhm.
done.
Yeah, so I'm quite sure the biggest field that these really lend themselves into is the deep learning application. So basically, if you can bring a factor of one order of magnitude or two orders of magnitude performance benefits, that means is in 3 years, this $1 billion cost to train is going to be divided by 10 or 100, right? And that's a lot of benefits for from a financial point of view. But equally importantly, if not more, I would actually argue more, but some people probably wouldn't. the environmental costs that are related with the training AI models, advanced AI models, is extremely high. And if you can reduce the footprint, carbon footprint of AI, deep learning operations by again a factor of 10 or 100, that's going to be incredibly impactful to the entire world, right? So the opportunity we have today with changing these compute elements is hopefully going to achieve both of them, and that is where I see them going the first. I really hope that the adjacent fields can use it to further improve what we can do scientifically and engineering wise, because I'm quite sure that it will open up new opportunities. But other than that, yeah, I think the primary one, at least I know what they can do, is towards much higher efficiency AI hardware, which we really desperately need.
Yeah, thank you. Oh, go ahead.
Thanks. Yeah, I was just saying thanks. That's great. The environmental costs are so very important. Anyway, I'm done.
Yeah, I agree. Sorry, Joyce, to go over you. Yeah, I agree that the increasing efficiency for computation is really important. And um, is it a good time for you to start also because of the bill that was
The
passed to
CHIPS Act.
like, yes, to so
Yeah,
do you get, are you thinking of, or are you getting funding to start your company through like those initiatives? That would be really great.
I'm hoping so. The act passed very relatively recently, and although I think now the money is allocated, there is still a lot of gatekeepers and bureaucracy that needs to be handled, such that money actually flows into companies and to the people who will actually use it. A big chunk of it is then naturally going to go to processing front. So the big companies who can now increase their manufacturing capacity within the United States. But I am confident that some portion of it will actually find its way to emerging technologies within the United States, and such that technology development can accelerate. And in addition to the CHIPS Act, given that there is a very solid environmental cost angle to this, there are indeed some government initiatives that I'm hoping to get more involved in. And also, if there is anyone in the audience who knows them better than I do, I would appreciate if they can reach out and let me know who could be the people of interest that I can get in touch with. But yeah, there is definitely some governmental funding. There is also, of course, private equity interest there. Given they mostly are interested in the financial gains, to be fair, more than the environmental. And I don't judge them by any shot, by the way. A considerable amount of technology is developed thanks to commercial gains. So I have nothing against it. But yeah, so I'm basically trying to pursue both of them, whichever makes the most sense for now.
Yeah, I would imagine, wouldn't Apple be really interested to have this in their phone, especially because, I mean, you said room temperature. How about if a phone gets warmer than that? Is that an issue?
No, it is okay. So they could indeed be interested. We have some commercial companies reaching out after the paper was published, and they liked what they were seeing. So there is some commercialization interest within the existing companies as well, which is definitely a positive. Uh, Mobile, I'm not sure if these lend themselves the best. I think for larger scale places like data centers of Amazon, for example, it would probably make more sense. And currently, that space is crowded by NVIDIA. And so wherever you see very large racks of GPUs, I think those would be the initial places where these might start showing impact. Uh, but mobile might be maybe in the future, because the reason I'm saying that is the in order to get the most out of these systems, I think the on edge computing for training area allocation becomes quite significant. That's why most AI chips we see, I'm not going to say all because it's definitely not all, but most AI chips we see on edge do inference rather than training. And from my point of view, at least, analog lends itself to training much better than inference. So that's why I don't see mobile to be the most immediate application, at least, maybe in the future, but instead, companies like Amazon, who have large data centers, or Meta, indeed, whoever processes massive loads of information at those systems, they would probably be the earlier adopters of this technology.
Yeah, that's interesting. I didn't think of that. I was mostly thinking about decreased energy costs that would prolong the life of
Mhm.
batteries. So, that's always an issue for people, like the watches and stuff like that, to keep charging them. Because ideally, for the new features that are coming out and will come out, like blood pressure measurements and stuff like that, those make the most sense if you continuously, even during sleep, monitor that data. If you have to at night take it off to charge, which I guess most people do, to charge your watch and all these edge devices, the most crucial data you don't
Mhm.
get, like, and I see Apple going into the health
Mhm.
uh, system and other. So I was just thinking, of VR devices and whatnot, like if they could cut down energy costs, that would make
No, that
people
makes.
more
Sorry,
addicted.
sorry. I'm still getting used to the platform. My apologies. Please
Oh
continue.
no, I was rambling on. Like, so go ahead.
No, I was gonna say you are dead on this. You're 100% right. Edge devices and efficiency is a huge part of what they are doing, and as you exactly put right on, if you have to basically take it off to charge, you are really sacrificing quite a bit of the benefits that you could otherwise get, and elongating the lifetime of mobile and smartwatches and so on. It's probably the biggest consumer electronics challenge. I think much more than the cameras and displays that are already quite advanced, but batteries that are so easily drained and through cycling so easily degraded. But I think even though it is a very exciting application field, I think the technology is just not there yet to aim for inference first. And the reason I'm saying that is the device and system requirements you need for inference, which is basically to, you have a trained network and then you are just using it to, for example, analyze the data, right? You have this bodily parameters, and then that gives you, oh, okay, you didn't sleep well, for example. That kind of analysis, the inference applications as such, they need different requirements compared to training. So then you might need to choose which application that you want to aim for. And even though mobile is a huge field on its own, and edge devices and edge chips are a very valuable, big market to address there and big impact to get as well, uh, I think training is an easier market to put the existing technology in. There is a more synergy. There's a higher synergy between the existing state and the state that they need to go, that is required by the training applications. And B, actually think about it. You know, this GPT-3, the future GPT-3, let's say GPT-5, right? Let's say that comes in 2025. If it is going to consume indeed more energy, a higher power than New York City, we are talking about a massive data center that powers that. So cutting a fraction of even 1% there, let alone 10 to 100 fold, that makes a huge difference, right? So again, I wish they could be for all applications. I think that would be the best case, and maybe one day it will. After addressing training, maybe some advancements will come, and then inference will also become a obviously a useful deployment field. But at least from where I stand, and not everyone agrees, by the way, in this field. Some people in this field actually think inference is a better idea. It's just my opinion that training, large scale training examples is where these systems would be first adopted in, and probably give the most initial benefits, such that in order to justify all the development costs needed to get to that point. That's at least where I see it today.
Yeah, thank you. And another question that is from a very uneducated in this field background is: would your, at least the material that you're using, would you be able to make batteries out of it?
No,
Because
that's a good question.
you have,
Yeah,
oh good, because it doesn't degrade. It's not degrading, so it sounds kind of ideal. But maybe,
yeah.
yeah.
No, it is a very good question. So actually, if you go far back in time enough, there were some groups, although I don't know why not widely used, some groups were using it for microfuel cells. So not exactly an ion battery that we use today, but for energy storage purposes. I think that's what the key part of the question was. And as a protonic battery and protonic battery electrolyte, in microfuel cells, I think these can indeed be increasingly used. I mean, I am not a battery person. I actually find myself in this field of ionics by mistake. I didn't know that I didn't know anything about batteries before. Yeah, I mean, beyond any general knowledge, anyways, before I joined this field. But indeed, exactly as you said, from what we are seeing from these devices, there might be some good opportunity to use as a protonic battery electrolyte, or I don't know, even maybe lithium battery electrolyte. I really don't know. Given that the degradation is so minimal and the speed of ions that you can shuttle across is so high, uh, unless it's contradicting with some of the other properties that you need in batteries, which I might not be aware of, then yes, I guess so. I mean, I'm probably not the right person to answer that, but as a a general engineer, at least I can see at least there is some room for exploration, and I think that's all what we can hope for in the field of research anyway. So yes, I would say yes. PSG, we might see more in energy storage applications as well in the near future. Why not?
That's exciting. We had months ago, and I think Denise and Abyss, you were here, and you might have a way better memory than I do. We had a group that here as guest speaker that developed a way to charge batteries with quantum technology to charge batteries. Um, how many times, like, instead of hours, like usually like a Tesla battery you need like 10 hours to charge. With their system you need only 2 to 3 minutes
Wow.
for a battery size like that. And the cool thing is, the bigger the battery, the the higher the factor is of speeding up the charging speed. So if you have a very small battery, the acceleration of charge is still significant but less. But the larger the battery, the more significant increase in speed you will have. So I'm thinking of, maybe I'll write them and share this paper with them and ask them, what do you think? Because they developed this way of charging fast. The problem was, they had a few problems, and I forgot sadly the detail. Maybe I can share the presentation with you. And I kind of think if they would know about your hardware and the materials you're using, that this might be interesting for them and useful.
Yeah,
So,
that's a very good point. I mean, I
um,
was recently at a solid state ionics conference, which is not a place that I am, you know, not a place that I used to go before. But they were interested in the results, so I gave a presentation to them. And indeed, in the audience, there were quite a lot of people who were working in energy storage applications, some of which in batteries, some of which in fuel cells. And I think they already took some ideas, and I hope they can take even more. To be fair, because that's how science propagates, right? I hope they can take it and advance it as far as it can go. And then we are trying to also form some collaborations with some groups who have been working in the field of ionics for a long time. And again, most of these people are interested in energy storage primarily. So yeah, I really hope that there might be more overlaps with such people, such that they can bring their existing knowledge into this and see what we can do with PSG, how we can push it even further than where it is currently. And then who knows? Maybe to the earlier question by Joyce, maybe their primary application will be batteries, is what you suggested as well. And I would be very happy to see that happen, right? I would be thrilled. There are many other applications that, again, we can see possibly going, which is these smart windows is a big technology that have had some challenges throughout development. And maybe, possibly, I mean, this is pure speculation, by the way. This is on the speculative end of the educated guess, if I have to put it in the spectrum. Maybe they will be finding something interesting about the properties of this material and then integrate it. And who knows? Who knows? This material existed since by a long time, and even though it existed, not many people realized what if it could be used for this. And actually, a quick insight on how it became a reality. I knew hydrogen movement was actually a big problem for the early days of CMOS, right? So there was hydrogen residual hydrogen inside these oxides, silicon dioxide to be particular, and it was moving and it was causing all sorts of reliability issues, and they hated it. They wanted to get rid of it. So actually, my starting point was understanding what they did to get rid of it and do the exact opposite, such that it moves inside this material. So this material has existed for a long time. It was a problem for some people. It became a future for my application, and hopefully, people can start exploiting it further, and maybe adding some other dopants into it, or extracting some, or doing other flavors. I don't know, but it is exciting to even to speculate what might come after it. I think that's the joy of research, right?
Yes, I agree. And one more, you must be exhausted by now, but one more thought that I had that I think would be a really exciting future. We had a guest speaker here from Switzerland working on nuclear fusion, and he collaborated with the deep learning team from Google to improve the reaction of fusion. So basically, the AI made different shapes of this. It looks like a donut type of shape, and when it's like the ideal reaction, like the best one that we can achieve high temperature for a prolonged time. And the deep learning kind of went through different shapes and solving it in different ways that people didn't thought of before. But I think with your hardware, it might be, you know, it might be coming up with even, better solutions that, could generate a way of designing the reaction that one day fusion becomes actually, you know, the solution for all of humanity's energy problems and everything. And the thing is also the conductors, the semiconductors used for these reactors are also a problem. And yeah, I think it would be really interesting if you would there be a way that you could collaborate already with the hardware you have right now? like and simulate those reactions, that would be so cool.
I think, yeah, I mean, in the future direction, it's definitely something that would happen. Uh, Already not, unfortunately not. I mean, I think if you were to simulate that, it would take a very, very, very long time, even longer than what they already are doing. Since for simulation, you need to actually add things, whereas when it's happening, you subtract things. So but in the future, I think, yes, to your point, I mean, whether it's designing advanced engineering challenges such as fusion reactors, or designing drugs, which is where AI is very prevalent, drug discovery, uh, it is definitely a very big application field. I mean, actually, for drug discovery and in general pharmacology, quantum systems are also, it's one of the proposed saviors in order to come up with better drugs for for example, in oncology, right? So yes, I mean, these that is why we definitely need AI. So in the beginning, I was showing, okay, yes, training these systems are going to take $1 billion, but the reason at least we are still trying to push it forward is there is so much to gain through artificial intelligence. It can solve the energy crisis if they can find design a better fusion reactor, as your example. It can, if they can find a drug to cure cancer through drug discovery, then that's also one of the humanity's biggest problems solved, I guess. So what it empowers is extremely interesting, and that's why we need to find a way to keep pushing it. I mean, the other way to do was would be, okay, this is how much we can push it, and then let's stop. That's the amount of power we have, but we don't want to do that, because there is really so much to achieve with AI. So absolutely, they might come, but when these architectures are at full scale, when these architectures are fully powered and whatnot, and then yes, they will definitely be used in designing better systems for many things. And the example you gave is a very good one. I mean, it would definitely be a potential application field. It's just not there yet. I guess sometime will need to take place, but hopefully with the right understanding, which was one of the last slides I showed, is system as a whole understanding instead of compartmentalized engineering. We can get to there hopefully faster, and start making an impact early on, as early as possible.
Yeah, thank you for doing this work for all of us, for us humans. That is really important. I'm so glad you use your brain to do this challenging, but hopefully very rewarding for all of us in the end work. And we wish you all the funding for realizing this. Maybe, I don't know, maybe we can all write a letter to to the president, give him the money or something. Something like that. So feel free to reach out to us. And yeah, I thank you so much for coming and sharing your knowledge, what you are working on, and yeah, we wish you all the luck and all the best, and a great weekend too.
Oh, of course. I mean, it was a really pleasure. Thanks a lot for inviting me. This was a very nice experience. I really enjoyed it. Hope the rest of the audience did as well. And yeah, let's keep in touch. And also to everyone, have a great weekend.
Yeah, and please come back anytime if you have like updates or some research you want to share with us. Come, please feel always invited, and I'm glad you enjoyed it too. That's the best. If you enjoyed it too, then everything was great. So, and thank you
Awesome.
everyone for coming and interacting, asking questions. Yeah, Joyce, go ahead. You want?
I was just going to say thank you very much. This is very exciting. I hope you don't mind the background noise. I'm taking a walk.
No, not at all. Thanks a lot. Thanks a lot, everyone.
Great. Oh,
Thank
go
you.
ahead, Avis.
No, I was just gonna say thank you.
Okay, great. So yeah, thank you. Come back anytime. And yeah, and everyone, if you like discussions like this, follow the club. We will have more rooms with guest speakers in the future. I can't promise that it's just as exciting as today, but it's also Dr. Serrano. He's developing some photonic quantum technology, so we'll talk about his work next week. And then Nick Harner, he's marine biologist, and he will explain how sea sponges sneeze to dispose waste, and how they do that and why, and about his marine biology work. And then we will have a room about geology, how the inner core structure of the earth came about. So it's paleomagnetism with Dr. Tarduno. And on Friday, we'll have Dr. Valtteri Wikström talking about interbrain synchronization while people are online gaming. The brains apparently synchronize, although people are far apart from each other, not in the same room. So, yeah, thank you so much. Thank you, Murat, again. This was such an honor and pleasure. And bye, everyone. Thank you.
Bye.
Bye.
Close the room in 3, 2, 1. Bye, everyone.